up, Maz fans and YouTubers? This video is on hypothesis testing using correlation coefficients for finding correlations between pairs of sets of data. And of course, you know that you can plot scatter graphs and look at that type of thing visually. But we've also had in AS the correlation coefficient calculations where the value, if it's close to 1, indicates a strong correlation, and if it's close to -1, it indicates a strong correlation, but the plus and the minus would tell you that it's strong positive or strong negative. If it's close to 0, then you are saying you're closer to no correlation, or you have a weak correlation. But the problem is this: if you take a random set of data, which I've done, here it is, like so. Now this is randomly found values. There's no link between these pairs of values. I got them from random number tables and I've just paired them off. So they are, as I'm saying at the top here, randomly found values. Now we can work out a correlation coefficient for those randomly found values, and actually in this case it comes out to be minus 0.594. Now that indicates a moderately strong negative correlation, but we do not really have that because the values were found randomly. And so the problem is that your correlation coefficient, when you work it out, will not be 0. The chances of it being precisely 0 when you truly have no correlation is very, very, very small. And because we'll always be able to kind of ascertain some kind of pattern. So this is the problem. You can have a random set of pairs of values, and the correlation coefficient, as we have learned to work it out, will not come out to be 0. And in fact, you can go ahead and even plot these values, which is what I've done. And it still kind of looks like you might well have a pattern there. And so it's possible that we will look for patterns and find patterns where there isn't any. And not only that, but the correlation coefficient will also possibly make that mistake, if you like. To be perfectly fair here, I did get one other value in the data set that I haven't listed there. I have plotted it there, and what I'm doing is ignoring that as an outlier, which again in practice is what you might do. So it's true to say that if I did include that value in my correlation coefficient, then my R would be closer to 0. But what you might well do is choose to ignore that as an outlier. And so to illustrate this as best I can, I am ignoring that, which may well be done in practice, and then looking at the fact that the data then that I'm left with does look like there's possibly patterns or a pattern to it. But again, I would come back to the fact that those numbers have been picked randomly. So once again, to state the problem, you could have randomly paired off values where by definition you have no correlation, yet a scatter graph might suggest a correlation, and a correlation coefficient might also suggest a correlation. And as I've said before, one of the ills of statistics is that you make more of it than you really ought to. It's always a kind of summarizing of values and of data, and as such it's always kind of a dilution of the full picture rather than a concentration of it, which is the mistake that people tend to make. Now, hypothesis testing comes to our rescue here again, where we are dealing with correlation coefficients. We start with a null hypothesis always, that we have no correlation, That is R is 0. In some texts, the R is sometimes written as a Greek letter rho, by the way, but mostly that would look like this, kind of like a P. Mostly at A level they use R. I'm just going to use R for correlation coefficient. Now, we suspect, possibly with our random data, that we would have a negative, moderately strong negative correlation. So my alternative hypothesis here is that R is less than 0. In other words, that we have some kind of negative correlation. And there's 9 pairs of data points. I'm going to go for 1% here because that would be very fussy, and I'm going to be fussy because of the fact that I've fudged it slightly by taking out a point. But I can go to tables. Again, these tables are not difficult to use. You don't really have that many options here. At 5% level of significance, sorry, I'm not even going for 5%. I'm going to be more fussy and go for 1%. So I'm going to take more convincing that there is a correlation if I do that. And I've got 9 pairs of values. So my critical value is 0.7498. But what exactly does that mean? How is that used? Well, there's a picture. Our critical zone then on the correlation coefficient scale would be, it's plus 0.7498 on the tables, but because I'm looking for lower than 0 correlation, then I go into the negative part of the range and I make that value from the tables negative. Now anything smaller than that, then between that and -1, would be in the critical zone, and then it's going to have to be at least as big as that value for me to be convinced that there is some kind of correlation here. Otherwise, I'm going to stick with the idea that there's no correlation, which is my null hypothesis. So again, remembering my random data, I did work out the correlation coefficient to be minus 0.594, which is my test statistic in this case. And that is that point there. I haven't actually labeled it, but I'm taking that dot there to be my minus 0.594. There, and then my critical zone from minus 0.7498 down to -1. So anyway, I'm not in the critical zone, and therefore we hold on to the null hypothesis that we don't have any correlation. If we were not particularly inclined to believe a positive or a negative correlation, in other words, just that we're testing for some correlation rather than no correlation, then our null hypothesis and our alternative hypothesis setup is like that. And again, like before, we split the critical zone up then. If we're going to 1%, then we split it up into 2 0.5% at either end of the correlation coefficient range. That's what's known as a two-tailed test. The other ones are one-tailed tests. So it's a two-tailed test here. We've got to then look for a different critical value and make it plus and negative. In other words, we split that 1% up into 2 0.5%. We still have 9 pairs of data values, but our critical value now at either side of the range is 0.7977. At the negative side, we make it negative, and at the positive side, we make it positive, but it's that value. And then the critical zones are as I've highlighted there. It's not, I shouldn't really say critical zones. It's really still a critical zone that's just split into 2 pieces. And still, we're not in the critical zone here because our point again is there roughly, let's say, at minus 0.5-ish. Minus 0.594 it was. And again, that's not small enough there to be in that critical zone, and certainly it's not big enough to be in that critical zone or that part of the critical zone. So again, we're not in the critical zone, so we hold on to the fact that we have no correlation, and that we hold on to the null hypothesis. Okay, now I'm going to do this example quickly. I'll send you this sheet here. I don't want to use up too many of these good examples, but I will do question 2 here and then send you the sheet. Small bus company provides a service for a small town and some neighbouring villages. In a study of their service, a random sample of 20 journeys was taken and the distance x in kilometres and journey times t in minutes were recorded. So you're given some statistics there, the average distance and the average journey time and some other values that hopefully you can remember how to use those to work out the product moment correlation coefficient. If you can't, I have done it. Hopefully this will remind you. There's the data from the question. We're working out SXX and S. Really, I should have labeled that STT for this question rather than SYY. So those Y's should really be T's. And then I'll put my values in, again, XY, there should be XT, mean of the X's and the mean of the T's, where I've called it Y. But I get my values out, I've relabeled the Y's as a T there, and I put them into the formula and my correlation coefficient comes out to be 0.375. So that is part A of the question. And part B, stating your hypothesis clearly, test at the 5% level whether or not there is evidence of a positive correlation between journey time and distance. So that is based on that test statistic of 0.375. With this particular set of data, is that enough for us to think we're not just getting some random correlation coefficient based on nothing? As I've said at the start of this video, we will always do, but that we can consider it to be significant evidence of a positive correlation. So at 5%, you can look up the tables yourself. We don't need to split that 5% because we're strictly looking for a bigger or a positive correlation, bigger than 0. So we look into the positive part of the range. The critical value from the tables is 0.3783. Our test statistic, our R as it worked out, is unfortunately not quite big enough. Unfortunate anyway for the alternative hypothesis. It's 0.375. It's not in the critical zone, and therefore we will keep the null hypothesis. As said here, there is not enough evidence to assume a positive correlation, and so we'll stick with the null hypothesis that there is no correlation. Very quickly, I probably should have written out there at the start of this that my null hypothesis is that, and my alternative hypothesis is that, and therefore I'm looking for a correlation coefficient bigger than 0, some kind of positive correlation. So that's why I'm looking in the upper range of the correlation coefficient values.
I fill my mind up with ideas.